So lastly, let's see how Newton's method may be applied for multivariate nonlinear programs. So let's say our f now has n input variables, still is twice differentiable. Then all we need to do is to generalize the idea of single dimensional derivatives to gradients and Hessians. Okay, so I'm not going to go through all the details, but maybe you may understand. We are trying to give a function as the quadratic approximation of f at any given point. Okay, so we still want to do the Taylor expansion thing. It's just that now we are doing the thing on an n-dimensional space. So you still have f, first order derivative of f, and the second order derivative of f. It's just that the first order derivative now is gradient. And also your x minus xk is a vector now. So to multiply two vectors, you really need to take transpose of one of them. Your second order derivative now is Hessian. And this is a vector, that is a vector. So you need to do some transpose thing to eventually get just one value. Okay? So I hope you have some linear algebra background and you may evaluate that this is a scalar, this is a scalar, and that this somehow represents the quadratic approximation of f. Okay, so if you do that, then now we are ready to derive the formula for Newton's method. We will move from xk to xk plus 1 by moving to the global minimum of the quadratic approximation. And don't forget, again, what we are trying to do is to say, okay, for this particular function, suppose it has an upward curvature. Then we are going to global minimum by looking for the point where the gradient for this one is 0. Okay, so if it has a downward curvature, of course, it's just a weird solution, weird result. Okay, so if we want to have the gradient 0 here, then pretty much we are having this particular equation. So don't forget to do some analogy for this multivariate one with the previous single variate one. For the single variate one, your xk plus 1 is xk minus you do the second order derivative at the bottom and you do the first order derivative at the top. So here you still have the first order derivative. And to move your second order derivative somehow to the denominator, for matrix, what you do is to take inverse. Okay? So this may also be observed if you look at this equation. To solve xk plus 1, indeed you need to move something to the right hand side, and then you also need to take inverse for this particular Hessian matrix. Okay? So you may suddenly want to ask, well, how do I know the Hessian matrix is invertible? Oh, that's beyond the scope of this course. So as long as your function has a nice behavior, I mean your objective function, then your Hessian matrix would be invertible. But I'm going to ignore the details here. Okay, so now let's try to again do a numerical example. So let's try to minimize this function. So this function is a fourth order function. Let's say we want to solve this problem, and maybe you still have some memory about this function. So we may still do some analysis first. The optimal solution is 0, 0. And then we have our gradient, and now we don't want to just use gradient. We also want to use Hessian. So we first get our Hessian matrix. So let's say we start at a point which is BB for some positive B. Then you plug in BB into your gradient. So you get 8B squared, 8B cubed, 8B cubed. Or you plug in that to your Hessian matrix. So you get this. So then you may apply this formula. And then from BB, you are going to move to 2 over 5B, 2 over 5B. And if you try this again, you're going to see it becomes 2 over 5 square B, 2 over 5 square B. after you do one more iteration, right? So for this particular example, our xk may actually be expressed as a closed form function of k and b directly. So this is nothing but showing you if you want to apply the Newton's method numerically, what do you do? Get a gradient, get a Hessian, get the inverse of Hessian, get the formula, and then you're done. All you need to do and all the thing that you may do with with Newton's method is to get this formula and then keep updating until you converge. So finally, we have some remarks. For Newton's method does not have the step size issue. So that's one thing that is good. And in many cases, it may be fast. For example, Newton's method finds an optimal solution in one iteration if your function is already quadratic and having a minimum point. Okay? But unfortunately, it may fail to converge for some functions. Like in the previous example we shown, it actually may have an increment when you are doing the iterations. So that may be weird somehow. So a general short sentence for Newton's method is that if your function looks nice, if you know it has a downward curvature, it's just that you don't have a solution, then Newton's method may actually get to your optimal solution faster because it uses more information. It uses the second order information. But because there is no step size issue, so it's harder to control the process of Newton's method. Okay, so there are something good, there are something bad. For different situations, you may use different algorithms. There are certainly more issues in general. So nonlinear programming algorithms itself may be offered as a single semester course, and we don't have time, so we only stop here. What are other issues that people want to study in general? First, how may we guarantee that an algorithm may converge? What's the condition for us to guarantee convergence? Maybe we also need to do some analysis on convergence speed, because as long as you are talking about algorithms, you care about efficiency. Okay, but that's also too much, and we are unable to talk about this. But still, we gave you some intuition about how to compare the speed between gradient descent and the Newton's method. And sometimes you face non-differentiable functions, so you don't have gradient, okay? Then you need something else. So sometimes for some problems, people use subgradient, okay? Subgradient. So that's again something that we don't have time to talk about in this course. But anyway, there are some ways to deal with non-differentiable functions. And finally, of course, we need to have some way to deal with constraint optimization. But still, all I want to do for today is to give you some foundations for nonlinear programming algorithms for unconstrained problems. For constraint optimization, for this particular course, we are unable to give you any algorithms for that. But still, there are some analyses that we may do, and there are some insights we may obtain. We need to ask you to wait for further lectures. So for this lecture, we're pretty much done. Gradient descent, Newton's method, they may be used to solve unconstrained problems. And there are still a lot of things that we need to teach, but still we want to stop here to just give you the main focus and the main idea. So that's pretty much I have here. Thank you.